Well, we just seen that, well, for positive correlation and negative correlation only shows in the value of sign, which means when R is positive, that's positive correlation. When R is negative, that's negative correlation. The value of them, the absolute value regardless the sign, right? If they are more closer to 1, the linear relationship is more perfect. If the R value is more closer to 0, that we have weaker linear correlation, right? But the R is go closer to 0 doesn't mean the pair doesn't have any correlation. It possibly could have correlation by comparing these two, but it is just showing us the original data set paired data set. It doesn't have linear correlation. That's the only thing it showed us. Right. So next, let's see how we compute the R. So 3 things to be measured, n, which is be specified as the number of pairs. Since we are dealing with paired data, it's not like how many total value we have, we just count how many pairs we have. Then 3 things: some square error of x, or we just say some square error of x. That is originally was defined as the numerator. That is the error of x. When we sum the square, that is the sum square of error of our x, which that is by definition, which is we have seen is the numerator part of our variance of the data set. And then we calculate is just sum of x squared minus the square of sum of x over n, and sum of y, that is sum of y squared minus sum of y squared over n. And sum square of error of x, y, the interacting term, that's sum of x, y minus x, y over n. The R value will be the sum square of xy over the square root of sum square of x, sum square of y. And the key thing is for the R, we need to keep 3 digits of decimal. We have one special request in the last section, that for the z-score we need to keep 2 digits of decimal places using the general rounding rule, right? That if 4 or less, cancel anything afterwards, and 5 or more, we round up to the next, right? To keep 2 digits of decimal, right? Round to the nearest hundreds. Here for the R, we also have a special request that R, the value keep in 3 digits of decimals. Before everything we didn't specify, which means you could keep anything you want to, no matter how many places of decimal you want to. Everything, of course, more digits more accurate. But for the z-score, 2 digits we need to keep. For the R here, 3 digits of decimal. And another special thing is we say that x or y are coming from the numerator of the variance. So especially this thing have to be positive. second. Right, the first two have to be positive. The third one depending on the nature. Depending on the pattern of paired xy, which means if the pattern of xy after you draw is increasing, the sum square error of xy, the interacting term, have to be increased or have to be positive, not increased, have to be positive. If we get a pattern like that, we all have our SSXY to be positive. If we have a pattern like this, we have our SSXY to be negative. The sum square of error, the sign of it leads to the sign of r. If we observe the formula, the sign of r only depending on the numerator, right? The denominator is positive, have to be positive, then r to be positive if the interacting term error is positive, r is negative if the interacting is negative. Right, so that is our formula, and then that is our calculation of three basic things, right? Three sum square of errors, then we use those to find our r, a shortcut formula. Just break them. Right. Draw the scatter plot. And find the r. Zero, 10, 1, 11, 2, 11, 4, 2, 4, 4, 7, and 6, 5. Right, that is our paired graph, and from the formula we see, right, we need the sum square of x, which also the xy is the term we need, x squared is the term we need, and also y squared is the term we need. Right, they are the table, right? So to compute the r, we need that table. Right, before that, we may able to draw the paired. That x value is taking value from 0 to 6, y takes the value from 5 to 10. Right, and y value is taking all the way to 10. Right, the x and the y has the gap like that. Then we draw the pattern. I draw the scatter plot, which means just plot the point. When x is 0, y is 10. x is 1, y is 11. Well, we still have 11. Anyhow, rho x is 1, y is 11, x is 2, y is 11 also. X is 2, y is 4. Right, that's 4 points already. When x is 4, y is 7. And when x is 6, y is 5. That we looks like have a kind of linear pattern, but maybe not that strong enough linear pattern, right? That's what we can see. So we may expect the R to be negative, since we have a somehow the negative related trend over here, right? But maybe not that absolutely great value for our R. Right, so let's see what we will get. Fill in the blank of what we need. X, y is 0, is 11, is 22, is 8, and 28, and 30. The square of x just need to take the square of whatever we have. 16 and 36. The square of y is taking the square of y, right? 10 squared is 100, 11 squared is 120, 1. 4 squared is 16, 7 squared is 49, 5 squared is 25. Right, that are what we get. And then we add all together to get the sum of the table, of the column, which the first is sum of x, that we adding all together will get 15. You can use your calculator to add them. The second column is the sum of y, that is 48. The third column we get in the sum of xy, that I have on my notes, is 99. The next one is the sum of x squared, is 61. And the last one is sum of y squared, is have value 432. Right, that's what we have for the table value. And then before we apply the formula, we can just find out three things. Sum square of x, that is sum of x squared minus sum of x squared over n, which our n here we can observe that's 6, right, since we have 6 points on the graph, right, also. Which is sum square of x, sum of x squared, that's 61. Sum of x is 15. Divided by 6. 23.5. Well, 15 squared 225 divided by 6. Then 61 minus the result, whatever it is, we get 23.5 as the result. If you want to see the step, you could use calculator to find out the quotient before you subtract. 15 squared divided by 6, that's 37.5. Now we get 23.5 as the difference. Sum square of y, that's sum of y squared minus sum y squared over n. Right, the same thing you see if you're familiar with it already, is same thing as the numerator of the variance, that we get sum of the y squared is 432. Sum of y is 48. Squared divided by 6. (48) squared divided by 6 that is 384. And when we subtract, we will get 48. Right, for the SSY. Then the SSXY will be the value that sum of xy minus sum of x times sum of y over n. Which the sum of xy is the middle column of xy is taking the sum of xy, that's 99. Sum of x is 15, sum of y is 48. Divided by 6. And then we use calculator to find 15 times 48 divided by 6 is 120. That we get 99 minus 120 is negative 21. Right? At least this step agrees of what we have seen, right? That it should be negative for the r, and it should be negative for the SS some square error of xy. Right? That is the trend, depending on the trend of the points. Right, at the end, we have our formula r is sum square of xy over the radical of sum square of x times sum square of y. That is negative 21 divided by square root of 23.5 multiplied by 48. Right, I just omit the middle steps. So what we need to do is multiply and taking square root, then negative 21 divided by that result. We get negative 0.625. Keep the result again into 3 digits of decimals. Into 3 digits of decimals. This r again maybe looks like a negative 0.6, right? The absolute value is 0.6 something. Well, and from the graph, if we don't have this point, maybe it looks like a much stronger linear pattern, right? But with this point, maybe not as strong, right? And we see that the r is not that absolutely large number. Right, here absolutely means in the value of absolute value that's not large, right, which we get only 0.6 something. But we're not sure. Right? We can make sure when we see a way to compare with the thing. But anyhow, right, that is the full process of how we find out our r. Right, then the properties. Of r. R is the value between negative 1 and 1. In other words, r is always in between them. Right, when r is approaches to positive 1, that in the middle, let's draw a better graph. For the value of r, that has 1 and negative 1, the middle is 0. We have a positive correlation. We have a negative linear correlation. And the more closer to 0, that's more weak. Well, if our value is closer to the 0 part, that's a weaker linear correlation, and more closer to the 1 value, that's stronger, right? That's how we determine if we get a strong R or a weak R. But all the value has cutting between negative 1 and 1 for the R. Right? The below 0 is negative linear correlation, above 0 is positive linear correlation. Absolutely, if the R is getting closer to 0, that's weaker. If the R is closer to 1, absolutely, then they are stronger. And that's what the R can say. And also, R measure the strength we have seen already. The getting closer to 1 is stronger, absolutely. Getting closer to 0, absolutely, is weaker, right? But it is measure the strength of the linear correlation relationship. Right, it measures the linear relationship only. We cannot use it to measure something like parabola or something like exponential or logarithmic other type of correlation. It only measures the linear correlation of the pairs. Right, we have seen that, well, it can be only taking value from negative 1 to 1. How we determine, right? We'll use a table in our book. Use table A5. To determine the strength. Well, we have a table such looks like is the n value here, the alpha to be 0.05 and alpha to be 0.01. The top's a critical value. Critical values of the Pearson correlation coefficient R. Right, and indicates the number of pairs, 4, 5, 6, 7, 8, and so on. The alpha equal 0.05, they have values and 0.01 has another value which is bigger than that, which the critical value indicates that, well, if the R value is bigger than that critical value for the n to be 4 pairs, right, for example, 0.950. If our pair of data is 4, and we computed our R value is bigger than 0.950, then we say that pair is linearly correlated. And of course, if below that, it is not linearly correlated. And for the cutting value, it is also no, right? That is, the value need to be more extreme than that value, then we say it is linearly correlated. For example, for pointer 1, we have a more strict condition, right? Need to be R to be 0.990. And what we use is just the column of pointer 5 together intersecting with the 6 or 5 or 4 or 8, the number of pairs n, we get the critical value and we compare with the computed value. Use n. Right, to find the critical R value, then if computed R has value, if R is bigger than the critical value, then we have a sufficient evidence to support the claim of a linear correlation exists in between the population, right? In between the population. But anyhow, that's the critical value it refers to. Right, that if you see, right, the 6 and the alpha equal 0.05 is the example we did before, right, the sample size to be 6, and if we compute the R, that is 0.625, but critical need to be 811. Right, and something need to be clarified. The value here indicates the absolute value, as I mentioned a couple times already. In the symbol of two vertical lines around our computing object of our number, that is the absolute symbol, and that value indicates the absolute value here, that regardless the sign but only the strand is what we care about, right, to see how strong it is. In our example, right, we just computed our R to be negative 0.625, and from the table we found out the critical R, as I've graphed it over here, right, our N and alpha that intersect has the value of 0.811. What we can see is our absolute value of R is 0.625, and which is below the critical value of R. So we don't have evidence. No evidence to show that xy are linearly correlated. Well, you cannot show that they are linearly correlated. That is how we determine if R is strong enough. We'll see still in our later examples anyway. To see, well, maybe for some case that R is big enough. Right. So if a given connection of paired data are linearly correlated, which means R is big enough. Absolutely, of course. The regression line, sometimes it's called best fit line, sometimes it's called the least square line. Is the straight line that best fits the scatter plot of the data. So for some curve we can see maybe we get the line or the point is nicely patterned, that we are able to draw a line pass through it. That the equation we are set to be y of hat, since that interpreted or approximated, that is b0 plus b1 of x. b0 is this y-intercept, and b1 is the slope. We have each pair is xy here, and for different x we're able to pass the line there, that is y equals b0 plus b1 of x.